Welcome to today's lesson on evidence for climate change through time. In this lesson, we are going to look at how scientists know that Earth's climate has changed in the past and how they can compare past climate change with what is happening today. Climate change is not new. Earth's climate has always changed. There have been colder periods, warmer periods, ice ages, and times when ice sheets retreated. But the key question is not simply, has climate changed before? The better question is, how do we know climate has changed? And what makes modern climate change different? To answer that, we need evidence. Some evidence comes from natural records, such as ice cores and tree rings. These are called proxy data because they give us indirect evidence about past climates. Other evidence comes from historical records, such as paintings, diaries, and written descriptions of unusual weather. By the end of today's lesson, you should understand how scientists reconstruct past climates and why current warming stands out from natural climate cycles. Let's begin with the learning objectives. By the end of this lesson, you should be able to do three things. First, you should be able to identify the transition from the Pleistocene to the Holocene epoch. The Pleistocene was a period marked by repeated glacial and interglacial cycles. The Holocene is the warmer interglacial period we live in today. Second, you should be able to explain how ice cores act as proxy data for past climates. Proxy data means indirect evidence. Before humans had thermometers and weather stations, we still needed ways to understand past temperatures and atmospheric conditions. Ice cores help us do that. Third, you should be able to analyze long-term climate records to identify natural cycles and human-driven anomalies. An anomaly is something that differs from the expected pattern. In climate science, current rapid warming is often described as an anomaly because it is happening much faster than natural long-term cycles would suggest. So today is about evidence, patterns, and explanation. Before we go further, let's look at the key vocabulary. The first word is quaternary. The Quaternary is the current geological period. It covers the last 2.6 million years of Earth's history. During this time, Earth has experienced repeated cold and warm periods. The second word is interglacial. An interglacial is a warmer period between ice ages. We currently live in an interglacial period called the Holocene. The third word is chronology. Chronology means arranging events or data in the order they happened. This is important when studying climate change because scientists need to know not just what happened, but when it happened. The fourth word is anomalies. Anomalies are data points that are very different from the long-term average. For example, a sudden sharp rise in temperature after a long stable period would be a climate anomaly. These terms will help us explain how scientists study climate change over thousands or even millions of years. Now let's begin with the Quaternary Period. The slide asks, what if the ground you're standing on was once under 2 kilometers of ice? For much of the last 2.6 million years, large parts of Earth have moved in and out of ice ages. During colder periods, ice sheets and glaciers expanded. Large areas of land were covered by ice, and sea levels were lower because so much water was stored as ice. During warmer periods, ice melted and retreated. Sea levels rose, ecosystems changed, and new habitats developed. We currently live in the Holocene, an interglacial period that began around 11,700 years ago. This warmer period allowed human civilization to develop. Farming, settlements, and cities all became possible in the relatively stable climate of the Holocene. The key point is this. Climate change is not new, but the speed of current climate change is unusual. Earth's climate has always been dynamic, but modern warming is happening very rapidly compared with many natural changes in the past. Now let's compare glacial and interglacial periods. A glacial period is a cold period, often called an ice age. During glacial periods, temperatures fall and glaciers expand. Ice sheets cover large areas of land. Because so much water is locked up as ice, sea levels fall. This can expose land that is usually underwater and change coastlines dramatically. An interglacial period is a warmer break between glacial periods. During an interglacial, ice retreats, temperatures rise, and sea levels increase. This creates conditions where ecosystems can expand and, eventually, human civilizations can thrive. We are currently living in an interglacial period. The important idea is that the Quaternary has not had one steady climate. Instead, it has been marked by repeated cycles of freezing and thawing. These cycles show that natural climate change happens, but they also give scientists a baseline to compare modern warming against. One of the most important pieces of evidence for past climate change comes from ice cores. Scientists drill deep into ice sheets in places such as Antarctica and Greenland. Each layer of ice represents snowfall from the past. In some ways, it is like reading the pages of a history book, except the pages are layers of ice. As snow falls and becomes compressed into ice, tiny bubbles of air are trapped inside. These air bubbles are extremely valuable because they are samples of the ancient atmosphere. By analyzing them, scientists can measure gases such as carbon dioxide and methane from hundreds of thousands of years ago. The slide notes that ice cores can provide evidence from up to 800,000 years ago. Ice cores are called proxy data. That means they are indirect evidence. We did not have thermometers 800,000 years ago, but ice cores allow scientists to reconstruct past climates. They can show changes in temperature, greenhouse gas levels, and volcanic activity. So ice cores help us compare today's atmosphere with the atmosphere of the distant past. Let's check your understanding. The question is, why are ice cores such a valuable piece of evidence for climate change? Is it 1. They contain frozen fossils of ancient humans. 2. They provide physical samples of the atmosphere from thousands of years ago. 3. They prove that the Earth is getting colder every year. 4. They are the only way to measure current temperature. Take a moment to think. Remember, the key feature of ice cores is the trapped air bubbles. Those bubbles allow scientists to study what the atmosphere was like in the past. The correct answer is 2. They provide physical samples of the atmosphere from thousands of years ago. Ice cores are valuable because they trap tiny bubbles of ancient air. Scientists can analyze these bubbles to measure greenhouse gas concentrations, such as carbon dioxide and methane. They can also use the ice itself to estimate past temperatures. This makes ice cores one of the strongest forms of evidence for long-term climate change. The other options are incorrect. Ice cores do not mainly contain frozen fossils of ancient humans. They do not prove Earth is getting colder every year. And they are not used to measure current temperature. Current temperatures are measured using instruments such as thermometers, satellites, and weather stations. Ice cores are valuable because they help us understand the climate before modern measurements existed. Now let's look at another type of evidence, historical records. The slide mentions the Little Ice Age. This was a period between around 1300 and 1850 when parts of Europe experienced colder winters. We know about this from written records, paintings, diaries, and accounts of unusual weather. One famous example is the River Thames in London freezing over. During some winters, frost fairs were held on the frozen river. Historical records are not as precise as scientific instruments or ice cores, but they are still useful. They give us evidence of how climate affected real people and places. For example, if paintings show people walking or trading on the frozen Thames, that suggests winter conditions were much colder than they are today. The quote from John Evelyn in 1684 describes the river being frozen so solidly that people could walk across it. This helps confirm that regional climate shifts happened in the past. However, we should be careful. The Little Ice Age was not the same everywhere, and historical evidence often tells us about specific places rather than the whole world. Now let's look at one of the natural causes of long-term climate change, Milankovitch cycles. Milankovitch cycles are long-term changes in Earth's movement around the Sun. They affect how much solar energy different parts of Earth receive. One cycle is eccentricity. Eccentricity refers to the shape of Earth's orbit. Over very long periods, Earth's orbit changes from being more circular to more elliptical. This affects how close Earth is to the Sun at different times. Another cycle is tilt. Tilt refers to the angle of Earth's axis. When the tilt changes, it affects the intensity of the seasons. A greater tilt can make seasons more extreme. There is also a third cycle called precession, which is the wobble of Earth's axis, although this slide focuses on eccentricity and tilt. These cycles help explain the natural pattern of glacial and interglacial periods over thousands and hundreds of thousands of years. The important point is that Milankovitch cycles happen slowly. They operate over very long timescales, not just a few decades. Now we come to a very important idea, the hockey stick graph. When scientists look at temperature records over the last 2,000 years, they find that temperatures were relatively stable for a long period. There were variations, of course. Some periods were warmer or cooler than others. But after the Industrial Revolution, temperatures began to rise sharply. This sudden upward curve is often described as looking like a hockey stick, a long, fairly flat handle followed by a steep blade rising upwards. This sharp increase is a temperature anomaly. It stands out from the longer-term pattern. The slide also notes that current warming is happening much faster than the average recovery from an ice age. That matters because ecosystems and human societies can adapt more easily to slow changes than to rapid ones. If temperature changes happen over thousands of years, species and environments may have time to shift and adjust. But if changes happen over decades, adaptation becomes much harder. So the hockey stick graph is important because it shows not only warming, but rapid warming. Now let's check the key terms. You need to match each term with its correct definition. The terms are 1. Anomalies, 2. Interglacial, 3. Holocene, 4. Quaternary. The definitions are A. The current warm epoch that began 11,700 years ago. B. Data points that differ from the expected average. C. A warm period between two glacial periods. D. The most recent 2.6 million years of Earth's history. Take a moment to match them. Think carefully about the difference between Holocene and Quaternary. The Quaternary is the wider geological period. The Holocene is the current warm epoch within it. Let's go through the answers. Anomalies match with B. Data points that differ from the expected average. Interglacial matches with C. A warm period between two glacial periods. Holocene matches with A. The current warm epoch that began 11,700 years ago. Quaternary matches with D. The most recent 2.6 million years of Earth's history. These definitions are useful because they help us talk accurately about climate change through time. A strong GCSE answer should be able to say that the Holocene is an interglacial period within the Quaternary. Now let's look at another type of proxy evidence, tree rings. The scientific study of tree rings is called dendrochronology. Trees usually grow one ring each year. The width of each ring can tell us something about the conditions during that year. In warm, wet years, trees often grow more quickly. This creates wider rings. In cold or dry years, growth is slower. This creates narrower rings. By counting and measuring tree rings, scientists can reconstruct climate conditions from the past. Tree rings are especially useful for studying the last few hundred or few thousand years, depending on the age of the trees and whether old wood samples are available. They help scientists identify patterns such as droughts, warm periods, and cooler periods. However, like all evidence, tree rings have limitations. They are local rather than global, and tree growth can be affected by factors other than climate, such as disease, competition, or soil conditions. Even so, tree rings are valuable because they provide year-by-year evidence of past environmental conditions. Now let's tackle a really important question. If Earth has natural warming and cooling cycles, like Milankovitch cycles, why are scientists so certain that modern climate change is caused by humans? This is a key evaluation question. It is true that Earth's climate changes naturally. Milankovitch cycles, volcanic eruptions, solar variation, and natural greenhouse gas changes have all affected climate in the past. But modern climate change does not match the timing or speed of these natural cycles. Milankovitch cycles happen over thousands to hundreds of thousands of years. Modern warming has happened very rapidly, especially over the last 150 years. This timing is important because it lines up with the Industrial Revolution, when humans began burning fossil fuels on a much larger scale. Burning coal, oil, and gas releases carbon dioxide. As carbon dioxide levels have risen, global temperatures have also risen. Ice core records show that current carbon dioxide levels are extremely high compared with natural quaternary cycles. So scientists are not saying climate never changed naturally. They are saying that the current warming is too fast, too recent, and too closely linked to human greenhouse gas emissions to be explained by natural cycles alone. You might have said that current warming is unprecedented compared with natural cycles. That is a strong point. You might also have said that fossil fuel carbon dioxide directly correlates with rising temperatures. That is also important. Natural cycles, such as Milankovitch cycles, operate over very long time scales. They do not usually cause dramatic global warming over just a few decades. Proxy data, especially from ice cores, shows that carbon dioxide levels are at a quaternary record high. A strong GCSE answer might say, Earth's climate has changed naturally in the past due to factors such as Milankovitch cycles. However, these cycles happen over thousands of years, whereas modern warming has occurred very quickly since the Industrial Revolution. Ice core evidence shows that carbon dioxide levels have risen sharply, and this rise matches the increase in fossil fuel burning. This suggests that modern climate change is mainly human-driven rather than part of a natural cycle. That answer is strong because it acknowledges natural change, but explains why modern change is different. Let's finish by thinking about why this evidence matters. Understanding past climate change helps us predict future climate change. If scientists can see how Earth responded to previous changes in temperature, carbon dioxide, and ice cover, they can build better models of what might happen next. The past gives us a baseline. It shows us what natural climate cycles look like. It also helps us identify when current changes are unusual. That is why proxy evidence is so important. Ice cores, tree rings, and historical records allow scientists to extend climate knowledge far beyond the period of modern instruments. The key idea is this. To understand the future, we need to understand the past. By studying climate evidence through time, we can see that Earth's climate has always changed, but we can also see that current warming is unusually rapid and strongly linked to human activity.